Go.
Don't worry, you won't hurt my phone. Our friend the toaster.
Hey,
Okay,
hey.
this is what it's all about. Okay, so normally we'd have you guys do this in your notes, but today we're gonna be doing it and you're gonna be following along with me in your notes. So we're gonna go ahead and set up a circuit with 2 batteries, and we are gonna measure the current and the potential drop across the bulb, and then we're gonna draw a diagram and calculate the resistance and the power.
So make a diagram here.
Now, what will this look like? Okay, step into my office. Okay, so we've got our 2 batteries right here. Mr. Boykin, this book thing is smart. Just put the batteries in the book and they stay there.
Yeah.
Okay, so 2 batteries measure the current and the potential drop across the bulb. So this is set up nicely for us, right? We're gonna measure the current, it's in the flow right here. And then our potential drop will be, we'll just add these across the bulb. Right here. Got it on there. Is that on there? Good. Got trust issues with these clamps here. Okay, so
Well, they're alligator clips. They can bite you.
Okay, so Boykin, let's take a look at the current first, right?
Yeah.
Okay, and
That is 90 milliamps.
okay,
90 milliamps, 0.090 amperes, and I'm going to call that 3 volts. Well, 2.9 volts.
I dropped my thing in there. Okay, all right. So you said 90 milliamps.
Yeah.
So it's gonna be 91. It's gonna be 0.090 amps, right?
Yeah.
Okay.
And 2.9 volts. It didn't quite make it to 3 volts.
Yeah. So 2.9 volts. You can see my volts thing from the day before. Okay. So let me
All
go ahead
right,
and just
so now on your own, boys and girls, calculate what the resistance is of this bulb and the power of the bulb as it lit up. Go ahead, pause the video.
Okay, sweet. And this is what my drawing looks like.
Here we go.
If you used rectangle lines, it's fine. Okay. Now, did we want to do this with them?
Well,
Good idea. Just some experience.
you can put the
practice.
equation up for sure. The resistance is what? That's voltage over current.
Yeah. R equals voltage over current. And they want us to calculate the resistance. So it looks like we could solve for this, right?
Yeah.
Okay. And then it wants us to calculate the power. What's our equation? for
Intravenous.
power? Intravenous. I always use green for power. Power is intravenous.
So
boom.
the resistance is going to be 2.9 divided by 0.09, and the current is going to be 2.9 times 0.09.
It's a 9. Oh, wrong color. 0.090 amps times 2.9 volts. They're like opposites. Okay. All right, sweet. If you guys can plug those in, do the math. You got
Boom,
it.
boom, boom, you got it.
Okay, so here we go. Moving on to my next slide. Okay. Conventional current moves from the positive to the negative, and then we know that electrons flow from negative to the positive.
Now, we've been talking about electrons, and indeed in wires, it's electrons that are moving. The protons carry the positive. They can't go anywhere. But this conventional current is a historical remnant and actually has some utility when you get into integrated circuits and things like that.
It has a purpose at some level.
Yeah.
Go ahead and draw on the conventional current and the electron flow on your diagram over here.
Yeah, use a letter I with an arrow and an E with an arrow. You can do
You
this.
can do it, okay? All right, make sure you add that in there. This is a new thing.
Ah,
Well, resistance isn't a new thing, but we are finally giving the name a symbol. So the symbol for a resistance, well, actually, let me take that back. The symbol for a resistor is this here squiggly line.
why don't you change that light bulb into a resistor over there on your diagram?
Excellent, let's do it. So, if I was gonna make this into a resistor, I would simply go like that.
Boom, 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 done. It's simple, it's easy, it's the same. Behold, our friend the resistor.
Yes. Now, do we want to talk about like we know a bulb has resistance.
Well, yeah, and that kind of looks like the filament inside the little light bulbs. Yeah.
Right. But you'll start to see with the questions that we ask, they'll say a resistor. You'll draw it like
For
that.
example.
let's do it. Draw a proper circuit, with 60-volt battery, an ammeter, and that much resistance. I'm just gonna erase some things over here. Okay, so draw a proper circuit with a 60-volt battery.
Notice, boys and girls, we're asking you to do this over and over again. We're going to expect you to show us that you can do it on the quiz that's coming up very soon. Very soon.
Stay tuned. Okay, it's important that all of your lines connect. Okay, what's the next part say?
60-volt battery.
60 in the
12.5 ohm resistor.
12.5 ohm.
My name
Mary Tyler Moore.
Yeah.
Okay. And then our current is.
Well, what does the next slide ask us?
Oh, I'm like, I don't think it gives us one. Yeah, go with the current. Okay. And the power. Label the current and the electrical potential drop, and the battery polarity, power, and the resistance. Show the direction of. Okay. All right. So let me go ahead and erase this here. I'll leave that there. Oh, actually, mix these two.
You know what? I don't think we should do this for them. I think they should go ahead and do it. And if they have any questions, you can talk about it in class, don't you think?
I think so. So you guys are going to calculate the current. So you're going to figure this out.
Yeah.
Okay. That's the first step. And then you're going to calculate the power. Okay. So we want current. We want power. Okay. And then you are going to label is that the conventional? Just label the current on here.
Show both the direction of the electron flow and the conventional current. Don't you do it, they'll do it.
Okay, and then for this guy right here, it says label the current. So does that mean just put that
Oh, put that in your ammeter.
Yeah, put that in your ammeter. The electrical potential difference.
Put a voltmeter across the resistor and let them do it.
So voltmeter here. Okay, what should that read? Let's see, the polarity of the battery.
That's right.
Already got that in there. Okay, the power and the resistance.
Can you do this?
So that's what you gotta find. Okay.
All right.
Let's rock and roll here. Okay. So here is we're back to our toaster, and if you guys were here in person, you would have smelled the lovely toast smell that's emanating from it. Okay. So let's talk about our friend the toaster. So a 1200 watt toaster, Exhibit A, is plugged into an outlet.
120 volts.
A 120 volt outlet, and makes toast in not 1, not 2, but 3 minutes.
What can we know?
Exciting. What can we know just by looking at this?
Well, watts are the units of what?
Power.
Volts are the units of what?
Volts are a potential difference.
Minutes are the units of what?
Time.
So we got power, potential difference, and time.
Okay, so we know. Well, we know the power.
Yeah.
We could also calculate some stuff. We could calculate current and resistance, but what the heck? Let's go back to this power thing.
All right.
What is a watt? Like, what even is it? Okay, well, our watt represents power. That's our units for power, right? So if power is the change in energy over time,
And the units of energy are,
and the units of energy are joules per in seconds here.
so the power is a joule per second. So if this is 1200 watts, that's 1200 joules per second.
Okay.
So
Now,
if it's on for 3 minutes, what could we know?
it's on, we could calculate the energy,
Yeah.
right?
Solve this equation for delta E.
Okay, I'm just gonna look this up. Okay, so what did we say our this is from the previous slide. We said this was
1200
1200
watts.
watts, right? Let me actually just go ahead and rewrite this right here before we do anything fancy. Before I plug any numbers in, we said solve for our E, our energy. Okay, these cancel. Okay, so we
TP.
said our TP. I love it. We said our power was 1200 watts, right?
Yeah.
And then we said 3 minutes.
3 minutes. Let's see. 3
many
times
seconds is
60.
that?
3 times 6 is 100.
1 minute, 60 seconds. Okay, so 180 seconds.
180 seconds.
It was cancel. Yeah, seconds. Okay. 180 seconds. And that's going to give us the energy of this
Yeah.
system here.
And so a watt is a joule per second, so that's joules per second times seconds is going to give us joules.
So Boykin just said this is really a joule per second, right? And these cancel, so we're left with joules. We're all very happy. Now let's just go and throw this in the calculator. 180 times 1200 joules per second. How much energy is this?
Yeah.
It's a lot of energy. Your toast is demanding. Okay. So it takes that much energy,
216,000 joules. That's 216 kilojoules.
okay, for 3 minutes of toasting action.
Is that a lot? I don't know.
like a lot. I don't
Depends
know.
on how valuable toast is.
Yeah. Okay, so we knew that power, watts, time, seconds, and we can solve that for energy. Okay, we're gonna come back to it. All conductors have some resistance.
We saw that in that video about resistance. If you have current that's flowing through a wire, they're whacking into the molecules, and that resistance.
So even in these wires, as electrons flow through here, if we were to put our voltmeter, if we were to put it, oops, dang alligators, my left hand, come on, get on there. If we were to connect this up and put it on either side of this, we would get a very small,
Yep.
we would get a very small reading there, and
Because there would be some potential difference because there is some resistance in that wire.
Yeah, and so the same thing happens with the wires outside. I mean, any conductor, any metal that has current running through it.
Now, what you want is wires have small resistance, but there's still some there.
Yeah, the smaller the better, because some energy is lost by the charge flowing through any conductor. And why do we want it to be as minimal as possible? Well, the energy lost per second is power lost.
That's
by a
right.
conductor. Okay,
Yeah.
and what does that mean? The energy lost per second. The energy lost per second.
Yeah, and
It's
we
power
saw that
loss.
with these wires in this nasty toaster, is that the current was flowing through them. They had resistance, and it was using electrical energy and converting into heat and light. So
So it's almost like the energy lost from here. Is that what's heating up your toast here?
yes, ma'am.
Yeah, right? Okay. So sometimes it's important.
Yep.
Okay, so look at this equation. We are familiar with both of these equations.
That's
yes?
Ohm's law on the top.
Ohm's law, and this is our intravenous power.
Yeah.
Now, what if our potential difference is here? What if we went ahead and just put this right there? What would we get?
It'd be I times R.
Or I squared R. So power, in this case lost by resistance, is I square R.
Yep.
Okay, so that means we take the voltage completely out of the equation if we only have the current and the resistance.
And see, that's what the toaster is doing. When you turn it on, you've got a current flowing through those wires, and they start to heat up. It takes them a while to heat up.
Ooh, there you go. There you
And that resistance in these wires, nice and warm.
was
The resistance in the wires, you can see it's starting to light up now.
Yeah.
The resistance in the wires is converting electrical energy into thermal energy and some light.
Cool. Okay. All right, and homework for today, you are going to read. It's going to be chapter 22, page 520 to 522. And then on page 522, do number 14 and number 15.
Yeah, when you read, remember you might kind of drift off, and that's normal. Yeah,
Follow along with your finger to help you.
That's an excellent idea.
And if you forget where you are, go back.
And you can do this.
You got it.